His experiences, so let's welcome here.
Thank you for the invitation to speak today. As Dr. Payne was saying, I want to talk to you a little bit about our experiences in deploying MVAPICH on Beacon, and some of the testing we've done, some of the things we've seen. Give you a little bit of an introduction. The center that I run was founded in 2011. We're basically tasked with the emerging technologies and how to use that sustainably moving forward for science and engineering purposes. So we look a lot more at application side of things and trying to use easy-to-use tools for users to get the performance. Our primary work thus far has been on the Beacon project, which was originally funded by NSF and supported also by the state of Tennessee. In that project, we deployed a cluster. It was the first deployment of Xeon Phis that had 4 Phis per node. It was one of the earliest deployments of Phis as well at all. It achieved number 1 on the Green 500 in 2012. Currently, to date, we've had about 100 projects and almost 1,000 users. 60 projects have been pretty active in the batch system, and roughly a third of our users. And we've generated about, I think it's up to about 60 publications that have been reported today. So some of the interesting things when you add these extra mics, you end up with a whole lot of additional communication passed through the machine. And I'm not going to bore you by reading all these different paths, but the real issue comes from having an IB card, only having one rail of IB and having it on one sockets with 2 mics on the other. And the end result is we were originally seeing a pretty wide variance in performance with Intel MPI. Some of the later versions, more recent versions of Intel MPI seem to have mitigated some of that. From what we were told, the limitation was actually in the SandyBridge chipset itself, and it affected the RDMA across the different PCIe buses. So the MVAPICH team has been working on proxy to solve that problem, along with folks at Intel that did it as well as in a library form. And so we wanted to try it out and see if that helped us on Beacon, because we were seeing as much as an order of magnitude difference in performance across some of the different communication pathways. So, and last of all, based on previous experience, we expected MVAPICH to give us better performance if we tuned really well. So those were kind of the motivations for pursuing this, and we were very happy when Dr. offered for us to try out data and move forward with the team on this. So while we were doing the testing, there were several things we wanted to keep in mind. In particular, we wanted to make sure that we were using both MVAPICH and Intel MPI appropriately, so we had fair comparisons. We worked with the MVAPICH team. I'm pretty confident that we are using it to the best ability that we can on Beacon at the moment. With Intel, we worked with them off and on for several years now. We went back through and checked all the tuning. I'm pretty sure we're pretty solid there, but Carl, if I've screwed something up, let me know. We'll get it fixed. And most importantly, we want to know what we can recommend to our users relative to using the different APIs for different purposes. And hopefully be able to provide a set of guidelines and best practices for how to use those effectively. To start off with, we just wanted to verify benchmarks and look at what the general performance was on Beacon. So this is kind of the information that Dr. Payne was asking for. We ran a set including all latencies and bidirectional bandwidths. I'm only going to report bidirectional bandwidths here because it tells the story pretty much. The rest of the data is available if you want it. And we plan to use the benchmarks for regression testing when we make changes to the fabric or to the configuration or the API stack. Because in the past we've had some issues where upgrades on the Intel MPI or on the DSS have led to some rather dramatic changes in performance across the cluster. And so we've done it by hand in the past, but we're trying to automate that process a little bit more now. So this is just an example of kind of a what's going on question. So this is a test where we actually just did an InfiniBand communication. So it's just 2 ranks on the same mic. And you get over 6x better performance out of MVAPICH than we do Intel. Now I'm a little bit confused by that because in reality we're not going over IB or doing anything, right? So this is the result that leads me to believe that something may not be working exactly right with our current Intel config. Moving on, though, we start to look at the inter-node, inter-mic cases here. And these bottom lines, I know it's hard to read these graphs, and I apologize for that. I'll kind of point out the key facts here. But these bottom points here, this is the Intel performance, and what we've got is we've basically got the three key paths going through. So you've got it going from, in one case, going from first PCI bus through the IB link to the same PCI bus the IB card's on the other node. You've got it then hopping through to the second socket, and then you've got all the way through. So going from off bus with IB card through the sockets to the IB card through the network, and then mirroring that on the other side. And you can see that Intel basically gives you very, very similar performance regardless of which actual communication pathway that you're using, but that it's substantially lower than what we got with MVAPICH when we tuned it. So MVAPICH has a couple of different proxy settings. This particular test plot comes from using proxy mode 2, and this highest value up here is actually the case that corresponds to what proxy mode 2 was built to address. So, but you can see all of them perform roughly the same up here. After we did some benchmarking, we wanted to start to move into the application space, but we wanted to do it in a controlled manner. So what we did is we built a stencil app. Basically, it's a partition coordinator. It mimics what you see in a lot of field solves, where you're communicating boundary value data between ranges. We don't do any compute here. We simply look at communication because it made it easier for us to do tests. And in doing this, we wanted to look at several different things. We wanted to look at what sort of optimizations we need to do to get the best performance with MVAPICH. We wanted to look at how many ranks we could actually support on a given mic, and we wanted to look at the proxy settings. So in this plot, which is pretty busy, you'll see once again we get kind of the performance of MVAPICH that we were expecting based on the benchmarks up here. Unless we don't do the alignment of the buffers, okay? And then we fall off to these diamonds down here, which happens to be worse than the Intel values to begin with. So in this case, and that's kind of true what we'll see through most of the results. Intel seems to be pretty consistent and resistant to change. And MVAPICH seems to perform better most of the time, but you have to do it much more carefully. So in this case, we're looking at the number of ranks that we can actually support on the mic, and what we found was that the performance actually fell off very, very rapidly. This top line is 2 ranks, this is 4, this is 8, and once we pass that, we're below where Intel performs on all of its cases. So, one of the things we want to make sure we do is keep the number of ranks down to a very small number on each mic. So this is a comparison of the 2 different proxies, and you'll see here up top, diamonds are proxy 1, and so the best performance here is when we talk from the case that proxy 1 is set up for. So that's when you're talking from a mic that has an IB card on its bus to another mic on another node sitting on the bus with the IB card. And that gives us our maximum performance of just over 70 devices a second. Proxy 2 gives us pretty solid performance across the board for everything. It's about 6.5. So there's a little bit of loss there relative to proxy 1, but it works for every path through the machine. Whereas if you're running proxy 1 but not running on that bus, it falls off really badly for all the paths to the alternate bus. So as a result of this, we'll be configuring the default configuration around proxy 2 on beacon. And ultimately, it'd be nice to see some way to dynamically switch appropriately between the 2. So from this, we really learned that we had to watch our alignment on the buffers. It makes a big difference for MVAPICH. Didn't really affect Intel pretty much at all. We got to watch the number of ranks that we deploy on the card. and we're going to run proxy mode 2. So moving up from that, we've heard Lulesh a few times, so I won't go into a whole lot of details on it, but we moved up to Lulesh, which is kind of a mini app. It's closer to a full-scale application. We wanted to see how it behaved. And in this case, we actually profiled a little bit, used a trace analyzer and isolated the MPI communications associated with the all-reduced and the iSIMs, and looked at the performance difference for Intel versus MVAPICH. And you see about a 60% reduction in the communication cost, realizing, however, that MPI was actually only 3% of the runtime for this application, so you're not going to see a 60% reduction in wall clock. But all in all, this is a pretty solid result for MVAPICH here. From there, we move on to a full-scale application, and that's Genesis. It is a multi-physics code developed by Tony Mezzacapa and his team at Oak Ridge National Laboratory. They currently run full-scale runs on Titan, for instance, and a lot of other resources. And this is their development code. It's looking to replace kind of what they're using for production at the moment. When we looked at this, the breakdown was still, pretty similar to what we've seen before relative to the communication times here. But we didn't get any real performance improvement out of MVAPICH here. And when we started looking into it, we think it probably has to do with the fact that the buffer's online appropriately, but we haven't really had a chance to search deeply enough to know for sure. We'll be working with the team to actually try to identify that issue and see if we can improve it. So moving into another field of interest to us, because we're starting to do more and more in bioinformatics and computational biology. We want to look at MPI blast. Ultimately, we'll be looking at, we have a version blast that we're working on, that we've been working on for Intel. That's called HPC blast. It wasn't as interesting to look at because we've reduced the communication overhead to such a small amount that we really don't see a lot of change based on this. But with MPI blast, it uses a manager slave that is much more communication heavy than what we do. And so it's a different kind of communication pattern than we see with standard physics simulation, that sort of thing. As a result, you get some improvement, and it's about 20% faster when we're running 32 ranks on mic. Now this is a case where we would have loved to have run across multiple mics, but we ran into some errors with MVAPICH when we tried. So things are still not completely ironed out on Beacon when it comes to MVAPICH. We'll talk about that a little bit in a second. But, and in particular, this particular app actually continued to scale just fine, which was not the case with the Stencil app. So we could add more and more ranks without a problem. And a lot of that had to do with communication, topology, and inside the application itself. So the amount of data that's being communicated grows significantly for the Stencil app as you break it up more and more with domain composition. It doesn't change so much here because you're just basically sending small update messages. And another kind of final app that we're looking at to some extent here is P3D FFT. And this is the core distribution of it, so it's not a hybrid version or anything like that. It is a fast Fourier transform in 3D, but it uses a 2D pencil decomposition. So it's very similar to some of the large astrophysics codes and cosmological codes. So ENSO, for instance, uses the same sort of decomposition. That runs to scale. It ran to scale on Kraken, and it runs to scale on some larger machines now too. So any savings here actually maps to a pretty big savings in terms of science. So we get an interesting graph here. I'm not real sure about a few of these features, but what this is showing is it's showing 1 rank per phi with a fixed problem size. And what we're doing is we're increasing the number of nodes and hence the number of ranks as we go. So you get smaller message sizes as you scale the problem. It's a strong scaling test. And For this case, with a one-hop configuration, so we put the mic on the first bus of the big, we see that MVAPICH is 90% faster for these smaller messages, and or it has a 90% decrease in time, and there's a 40% decrease for the larger ones. So I'm not real sure what exactly happened in Intel MPI to cause that. I don't know if we changed communication modes internally or something, but that definitely merits a little more exploration. It will almost definitely merit an email to Intel about it, because it's worse here. So when we move to the two-hop configuration, this is where we see the benefit of Intel's being pretty consistent across all of the sockets, whereas MVAPICH is not. And there's two, and we wanted to run P3FFD with the proxy-2 as well. But this is a case where, once again, we ran into some InfiniBand errors. So we weren't able to get it to actually execute on beacon correctly. So as a result, we're presenting the proxy-1 config, and this is just what it looks like. This is kind of a what if we misconfigure the proxy kind of situation. And you can see that it's a significant difference in performance there for MVAPICH. And so you really do need to pay attention to that on beacon. And I think having the extra mics, having the complexity of the communication house, kind of creates a little bit more difficult problem, probably also for the developers for sure, but also for the users. And ultimately, most users are probably going to just throw the ranks on these mics as if they're all equivalent. They're not really going to think about the differences in the architecture. And that kind of pushes the importance of handling that appropriately, either through best practices documents or preferably in the MVAPICH distribution itself, right, to the forefront, so that the users don't have to think about subtle differences in the architectures at different times. And I think that's going to become even more important as we move into exascale and see even more different types of changes at different varying levels of hierarchy in the overall system architecture. So overall, what we're looking at here is some observations, and MVAPICH performed really well on all benchmarks, which I expected to do. The performance on benchmarks, we can carry some of that over into applications. It carried over best when the applications were fairly straightforward and mapped closely to some of the benchmarks. We had to pay very close attention to several details, cache, proxy, ranks, things like that. But then some applications we just had problems with on beacon, and I'm not sure why yet. We haven't had a chance to really sort it out. But we ran into essentially a bunch of InfiniBand errors for various cases with these different applications. So P3FFD didn't run between mics or between nodes when the proxy was set to 2. The MPI blast didn't run between nodes to mic cases at all. And Romax, we couldn't get it to run yet at all either. And so, looking at this, one thing that we come away from it with is that it's not as simple as changing the module file out and recompiling to see magical performance increases out of an optimized MPI. You're going to have to do some effort to get it to that point. And, as I said earlier, that can be challenging for a huge cross-section of our user space. I think that's less the case when you start looking at the DOE and some of the labs and some of the high-end users. But in NSF land, a lot of them aren't going to be prepared to do those sorts of optimizations themselves. So I think it would be useful if we're not able to get MVAPICH to deal with it internally, to have some sort of mechanism to help people auto-tune for MVAPICH, or at least a set of a good solid document best practices or something to give people a starting point. That was something that we kind of, we started running, and we're not the average users. We're computational scientists, and we still ran into a few problems here and there. And it's not that there wasn't documentation. The documentation as a whole is very good. It's just not necessarily easy to always find what you're looking for in a very clear, concise guide. And I think that's probably the piece that I keep away from relative to the user space that they most important. It did provide significant performance increases, and that's very attractive, and we'll absolutely be working to optimize Beacon and MVAPICH2 to work together to solve problems more effectively. You know, it would be nice if it was more consistent relative to its performance across the different configurations, kind of like Intel is. But I suspect that there's probably some trade-offs there that make it difficult to achieve the performance that you get without some of that variability. And in particular, another thing that would be nice for Beacon is some way to actually address all of the mics appropriately with the right proxy, and have that auto-detected and mapped effectively based on whichever path they're communicating with at any given time. And I'd like to acknowledge the help that we received from the MVAPICH team. It has been excellent. It has been very, very rapid, and it was crucial to getting some of the results done that we got done. And to Dr. Pina for all the support and the opportunity to speak here. And also to Intel for all the past and present support we've had deploying and operating Beacon. So, with that, if you have any questions.
Okay, let's ask any questions? Yes.
So I'm from Intel, and I have been working on the proxy stuff. I was just on iron, so I was wondering if you thought the proxy running with Intel MPI?
I think it is.
Okay.
Well, okay. Let me scroll back a second. So the last time, I need to check that probably.
Okay.
To be sure. It may not be in the current version. When did the proxy come in?
He said that with 5.0.3 it was supported already, but you needed to set some environment variable to turn it on because otherwise it eats CPU, right?
That may be exactly what the case is.
Yeah.
We tried to use the MPI tuning tool to identify some of those environment variables, but we've had problems getting it.
Yeah, so if you want more help from Intel,
Is Karthik the one that's been doing it? Or, I know you were a proxy originally.
No, Karthik's proxy was different because his was based on the MPI profiling interface, and his approach was mainly from the research side, just to see what to do to speed it up. But the Intel MPI product team is also working on that, so I'd be happy to put you in touch with.
Sure. So I would love to talk.
Yeah, we can
just
just
make sure.
have
As I said, I suspect that there's probably an issue there when I saw some of the numbers. But you know, this is one thing I'll say to that though, right, is that this is what's going to happen if the average user configures.
I completely agree. I completely agree.
So that's one place where I'll say maybe you might want to make it a little bit clearer and have better best practice.
I think better contacts with engineers will also help, right?
Sure.
That you're able to directly contact with the engineering team.
Sure.
Yeah. Okay.
Sure.
Any other questions? Yeah, so just say, I think some of these issues, I think we'll be able to resolve it. I think his system is a very unique system, the 4 mics. Okay.
Yeah.
I think that's what a lot of these systems, even the GPU side also, we are seeing 8 GPUs, 16 GPUs. So broadly, it's a lot of like affinity, how the affinity is working, how they're communicating with IE. One has to really understand these systems a little bit more details, and then see how to abstract it out. And I think this is not just a Intel MPI or MVAPICH2, I mean, all MPI stacks are, I think, going through the same issues. The machines are becoming exotic, and the stacks need to be intelligent. Okay, intelligent in the sense it has to automatically detect all these things and tune appropriately. And sometimes it is easy, sometimes it is hard. Hard in the sense it has to be experimented for a long period of time, having access to the machines to make sure where are the trade-offs. Because there are so many protocols, and I think yesterday in my tutorial I had shown like mic system, GPU systems. These days there are 11 to 12 paths, communication paths are there, and more number of devices are there. In fact, that expands. So the question is, okay, how best you optimize all these paths? And that is for only point to point. Then it goes to collective, then it goes to application. So I think this is a phase I think the community is going through. So I think we'll be very happy to work with you guys and see what kind of things happen to that.
Sure. Well, we'd be happy to extend access and accounts to anyone.
Sure.
In working on this. I know a number of folks at Intel already have access. I don't know if the right folks at Intel have access.
Sure. Okay. Any other questions? Okay, so if not, what we'll do is before the launch, we have done it in the earlier years, we'll take a group photo. So I think the way we do it, just it will be outside of the building. So people will guide you, so just go outside and then go right and then left. So we'll assemble in 5 minutes and let's take a photo and then come back, have the lunch. And then after that, I think 1 o'clock we'll start with Gilad's presentation. And I say this like we have so many people, this is a group communication. We have to go there, it's a barrier thing. So we have to go, let's see how fast we go there and then